Right, this is the walkthrough for the Year 12 Easter assessment. I'll start off looking at the mechanics, show the question, work through it. Okay, so question 1. We're given the initial velocity, so at time t equals 0, parachute falls vertically from rest, so my initial velocity is u. I know how high above the ground I am, I know how long I've been falling for, and it gives me the value of g, an approximate value of g. So for 1 mark, find the speed at the instant the parachute opens. Okay, so question 1, I'm given, I want v, I'm given that a is minus 10, because remember I always use up as my positive direction. U is 0, t is 3. I'm going to use v equals u plus a t. U is 0, so minus 30 meters per second. It wants speed, so the speed, remember, is just the magnitude of the velocity. There you go. So that's straightforward, 1 mark, part A. Right, part B tells, what does it tell? Let's have a look at it. When the parachute is open, the parachutist continues to fall vertically, decelerates at 12 meters per second for 2 seconds. Sketch a speed time graph. Well, I've got to use my brain a little bit. If I'm going at 30 meters per second, and I'm decelerating for 12 meters per second every second for 2 seconds, I'm losing velocity. I'm losing 24 meters per second in total. So I'm going to go from 30 down to 6. So this is going to be my speed in meters per second. This is time in seconds. I know that start at rest, when t is 3, my speed is 30 meters per second. That's from the first part of the question. So the first part of the graph looks like so. I don't necessarily need to work this out. I know that it's for 5 seconds, the gradient now is going to be minus 12. So if my height is, my width is 2, minus 12 is 2 times the height of this section. So of course it's going to go down to minus 6. So it's going to go down to 6. So let's do that there, because it loses 12 meters per second each second. So that has a height of 6 there, and then what does it say? Let's look back at the question. Constant speed and reaches the ground with this speed. So it's constant speed from here, so my acceleration is 0, i.e. the next segment is just a horizontal line. And it takes t seconds overall, so there's my big T there. I know that the total distance fallen is 550 meters, so there's B. For C, the area, the total area, is going to be 550, remembering that the total area covered, sorry, the total distance covered is the area under the graph. I'm going to split this graph into a triangle, a trapezium and a rectangle. So I know that the total area is a half base times height, plus the trapezium, remember it's a half the sum of the parallel sides times the distance in between, so 2 times 6 plus 30. And then I've got a rectangle here, 6 times t minus 5. And if I solve that equation by just typing it into the calculator, 550 equals a half of 3 times 30 plus half, of 2 times 36 plus 6x minus 5. Solve. It gives me 83 to the nearest whole number. 83 seconds to the nearest second, which is what the question asked for. Is that it for question 1? No. Okay, in a refinement, we're including air resistance. What would that do for T? Well, clearly she wouldn't fall as quickly, so the new T would be longer or greater than the found value. So T would be greater or bigger, or whatever you want to say, than the value found. And the last part says suggest a refinement, and I think the obvious thing, the way to tackle these is you go back and you look at the modelling. Parachutis's models of particle, we could comment on that. I'm going to comment on the acceleration due to gravity being modelled as 10. Because clearly we could use a more accurate approximation for G. So that's what I'm going to say for my final mark. Use a more accurate approximation for G. Is it approximation? Not sure that it is. Use a more accurate value for G. Question 1 done. Let's have a look at question 2. Okay, so the text just describes the model. We like a show that. Tell you what, I'll make this bigger. So you can see most of the text there. If you want to, you can pause the video. Text describes the model, as is often the way. Clearly what they don't do is put tension on the string, so I'm going to just quickly sketch this and put my tensions on. So you can have a read of that while I'm sketching. I'll pause it. Okay, so I've got the diagram here. I'm going to add the tension. Remember that the tensions, they always come in pairs, and they are equal and opposite. Not forgetting, of course, the force, the weight of Q, 0.6 G. Now this question is a significant number of marks, so there's a significant amount of work to do. I'm going to apply Newton's second law, and how we say that we do that is we just resolve in the horizontal direction. So for P, I'm going to resolve in the horizontal direction, and I'm calling that my positive direction because that's the direction P is going to move, which means that's the directions Q is going to move, so that's also positive. So for P, remember what we do, total force is mass times acceleration. So T, there's no force acting in the negative direction, equals 0.8a, equation number 1. For Q, I'm going to resolve in its positive direction of movement. Again, apply Newton's second law. 0.6 g is positive, minus t, because that's acting in the negative direction, equals 0.6a. And I'm happy with that. Remember what we get? We always get t and minus t. We always get pairs of t that are going to cancel out when I add them. Looks like the camera's a little bit out of focus, but I think you can see that. The method now is always the same. Add the two equations together, Of course, t and minus t are going to cancel out, so I'm going to get 0.6g equals 0.8a, 0.6a, 1.4a. A then is 0.6g over 1.4. G, remember, we're using a value of 9.8, so 0.6 times 9.8 divided by 1.4, which should be 4.2. 0.6 times 9.8 divided by 1.4. Look at that, 4.2, brilliant. Equals 4.2 meters per second squared. Done. Yeah, we like show that's. Okay. The next part is 6 marks. Find the time taken by P to hit the pulley from the instant when P is released. So just think about what's going to happen here. When Q hits the floor, the string goes slack, tension's going to disappear, so P is no longer going to be pulled along. Because that tension's gone, the acceleration will change. So we need to do 2 Suvat equations because acceleration changes, and remember the Suvat equations are called equations of constant acceleration. So consider particle P. Remember that's the one on the table. And I'm going to consider it before Q hits the floor and after Q hits the floor. Before collision, what I need is the velocity that P is travelling at the point when Q hits the floor, and I'm going to use that velocity for the initial velocity after Q hits the floor. So before collision, I know S is 0.4 because it travels the same distance as Q because the string is inextensible. I know A is 4.2 because we were told that. The question wants the time, and we also need the velocity to be able to do the second part of this question. So let's work out the velocity first. V squared equals U squared plus 2/8s. Well, U I know is 0 because it starts from rest, because the question tells me it starts from rest. 2 times 4.2 times 0.4 is, times by 2 times by 0.4, 84 over 25. So V is the square root of 84 over 25, and I'll leave it like that because it's accurate. To find the time, well, I won't use V because I've just worked it out and it might be wrong, so I'll use what I've already got. S equals UT plus half AT squared, 0.4, U is 0, half of A is 2.1, 2.1 T squared, so T is 0.4 divided by 2.1 square root of that. 2 root 21 over 21. And again, I'll leave it like that because it's accurate. After collision, well, after collision, there are no forces acting on P. So if we think about P's on the table, the only force is its weight, which we're not using in this question. So if I resolve horizontally, F equals ma, well, the total force is 0 because there's no friction because it's a smooth table, there's no tension, so 0 is 0.8a, so my acceleration must be equal to 0. So I'm going to do Suvat again. S-U-V-A-T. A is 0, time is what I want, velocity, don't care about. The initial velocity is the final velocity that I worked out before, so root 84 over 25. And S, well, I've already travelled 0.4 metres, I know it's 1.5 metres in total, so the distance left to travel is 1.1 metres. And I'm going to use S equals UT plus half AT squared again, s equals ut plus half a t squared. 1.1 equals the square root of 84 over 25 times t. A is 0, so t is 1.1 divided by root 84 over 25. Let's type that. Square root of 84 over 25, and it gives me an exact value. T is 11 root 21 over 84. Just fit it in at the bottom of the page. Total time is 11 root 21 over 84 plus the time from the first section, 2 root 21 over 21. Let's add that on. 2 root 21 over 21, and we'll go for 1.04 seconds to 2 dp. 1.04 seconds to 2 dp. Nice question. I think that's it. Let's just check. Last part. State one limitation of the model that will affect the accuracy of your answer to part A. So again, we look back and consider what could be more reasonable, and the thing that jumped out to me is a smooth horizontal table. There won't be any absolutely smooth surfaces, so friction will be greater than 0. So for part C, I am going to have to go onto another page. Okay. So for part C, the table wouldn't be absolutely smooth. You could say something like the rope wouldn't be absolutely inextensible, or the pulley would not be absolutely smooth. There would be some friction affecting the movement of the pulley. Question 3. So we're given an expression for the velocity. I'll just write that down and then take the question paper off the screen. So part A, we need to recognise that acceleration is the derivative of velocity. So if I differentiate 4 minus 2t, rest means that velocity equals 0. So let's solve this quadratic. I'll just move them all onto this side. I think this would factorise, well, it does factorise. 6 and 2 minus 6 plus 2. So t equals 6, t equals minus 2. Now we know it's time, so we discount the negative values. So time equals t equals 6. So the acceleration when t equals 6 is 4 minus 12, which is minus 8. They want the magnitude. The question says the magnitude of the acceleration, so we ignore the negative here. So the magnitude of A is 8 meters per second squared. And they often use the magnitude because positive direction is an arbitrary thing. Part B, the distance between t equals 0 and 3. So for part B, we need to recognise that the distance travelled is the integral of the velocity, and I need to go between 0 and 3. T values are 0 and 3. So remember the process, square brackets, integrate 12t plus 2t squared minus t cubed over 3 between 3 and 0. Substitute in my upper limit, substitute in my lower limit, which I can see will be 0, and then subtract. And I'll use my calc button because the calc button is your friend. 12x plus 2x squared minus x cubed over 3. Calculate when x is 3, 45. And for completeness, I'm just going to put in take away what I get when 0 goes in, but of course that's 0 because every term has a t. 45 meters because everything's measured. V is giving us meters per second. And I think, let's just check. Yeah, that's your lot. Okay, hope that's helpful. See you next time.